Let's take a look at RSA, a widely used algorithm for encrypting data. Encryption algorithms like Caesar and Vigenère ciphers aren't very secure. With the Caesar cipher, an attacker only needs to try 25 different keys to get the message's plaintext. While the Vigenère cipher is more secure than the Caesar cipher because of the larger search space for keys, once an attacker knows the length of the key in a Vigenère cipher, which can be determined via an analysis of patterns in the encrypted text, the Vigenère cipher is not that much more secure than the Caesar cipher. RSA, on the other hand, isn't vulnerable to attacks like this. The Caesar cipher and Vigenère cipher use the same key to both encrypt and decrypt a message. This property makes these ciphers symmetric key algorithms. A fundamental problem with symmetric key algorithms is that they rely on the one encrypting and sending the message and the one receiving and decrypting the message to have already agreed up front on the key they will both use. But we have a bit of a startup problem here. How do two computers that want to communicate establish a secret key between them? If the key must be secret, then we need a way to encrypt and decrypt the key. If all we have is symmetric key cryptography, then we've just come back to the same problem. RSA, on the other hand, uses a pair of keys, one for encryption and another for decryption. One is called the public key, and the other is the private key. The public key is used to encrypt messages. As you might guess by its name, we can share our public key with anyone we want without compromising the security of an encrypted message. Messages encrypted using a public key can only be decrypted with its corresponding private key. So while you can share your public key, you should always keep your private key secret. Since the private key should be kept a secret, and only the private key can be used to decrypt messages, if two users want to send messages encrypted with RSA back and forth, both users need to have their own public and private key pair. Messages from user 1 to user 2 only use user 2's key pair, and messages from user 2 to user 1 only use user 1's key pair. The fact that there are two separate keys to encrypt and decrypt messages makes RSA an asymmetric key algorithm. We don't need to encrypt the public key in order to send it to another computer, since the key is public anyway. This means that RSA doesn't have the same startup problem as the symmetric key algorithms.
So if I want to send a message using RSA encryption to Rob, I'll first need Rob's public key. To generate a pair of keys, Rob needs to pick two large prime numbers. These numbers will be used in both the public and private keys, but the public key will only use the product of these two numbers, not the numbers themselves. Once I've encrypted the message using Rob's public key, I can send the message to Rob. For a computer, factoring numbers is a hard problem. The public key, remember, used the product of two prime numbers. This product must then have only two factors, which happen to be the numbers that make up the private key. In order to decrypt the message, RSA will use this private key, or the numbers multiplied together, in the process of creating the public key. Because it's computationally hard to factor the number used in a public key into the two numbers used in a private key, it's difficult for an attacker to figure out the private key that will be necessary to decrypt the message. So now let's go into some lower level details of RSA. So let's first see how we can generate a pair of keys. First, we'll need two prime numbers. We'll call these two numbers P and Q. In order to pick P and Q, in practice we would pseudo-randomly generate large numbers and then use a test for determining whether or not those numbers are probably prime. We can keep generating random numbers over and over again until we have two primes that we can use. So here, let's pick P equals 23 and Q equals 43. Remember, in practice, P and Q should be much larger numbers. As far as we know, the larger the numbers, the harder it is to crack an encrypted message. But it's also more expensive to encrypt and decrypt messages. Today, it's often recommended that P and Q are at least 1024 bits, which puts each number at over 300 decimal digits. But we'll pick these small numbers for this example. Now, we'll multiply P and Q together to get a third number, which we'll call n. In our case, n is equal to 23 times 43, which is equal to 989. So we have n equals 989. Next, we'll multiply p minus 1 with q minus 1 to obtain a fourth number, which we'll call m. In our case, m is equal to 22 times 42, which is equal to 924. So we have m equals 924. Now, we'll need a number e that is relatively prime to m and less than m. Two numbers are relatively prime, or coprime, if the only positive integer that divides them both evenly is 1. In other words, the greatest common divisor of e and m must be 1. In practice, it's common for e to be the prime number 65537, as long as this number doesn't happen to be a factor of m. For our keys, we'll pick e equals 5, since 5 is relatively prime to 924. Finally, we'll need one more number, which we'll call d. D must be some value that satisfies the equation d e is equal to 1 mod m. This mod m signifies we'll use something called modular arithmetic. In modular arithmetic, once a number gets higher than some upper bound, it will wrap back around to 0. A clock, for example, uses modular arithmetic. 1 minute after 1:59, for example, is 2 o'clock, not 1:60. The minute hand has wrapped around to 0 upon reaching an upper bound of 60. So we can say 60 is equivalent to 0 mod 60, and 125 is equivalent to 65 is equivalent to 5 mod 60. Our public key will be the pair e and n, where in this case, e is 5 and n is 989. Our private key will be the pair d and n, which in our case is 185 and 989. Notice that our original primes, p and q, don't appear anywhere in our private or public keys. So now that we have our pair of keys, let's take a look at how we can encrypt and decrypt a message. So I want to send a message to Rob. So he will be the one to generate this key pair. Then I'll ask Rob for his public key, which I'll use to encrypt a message to send to him. Remember, it's totally okay for Rob to share his public key with me, but it would not be okay to share his private key. I don't have any idea what his private key is. So we can break our message m up into several chunks, all smaller than n, and then encrypt each of those chunks. We'll encrypt the string CS50, which we can break up into 4 chunks, 1 per letter. In order to encrypt my message, I'll need to convert it into some kind of numeric representation. So let's just concatenate the ASCII values for the characters in my message. In order to encrypt a given message m, I'll need to compute c is equal to m to the e mod n. But m must be smaller than n, or else the full message can't be expressed modulo n. So we can break m up into several chunks, all of which smaller than n, and encrypt each of those chunks. Encrypting each of these chunks, we get c1 is equal to 67 to the 5th mod 989, which is equal to 658. For our second chunk, we have 83 to the 5th mod 989, which is equal to 15. For our third chunk, we have 53 to the 5th mod 989, which is equal to 799. And finally, for our last chunk, we have 48 to the 5th mod 989, which is equal to 975. Now we can send over these encrypted values to Rob. So here you go, Rob. While our message is in flight, let's take another look at how we got that value for D. Our number d needed to satisfy 5d equals 1 mod 924. This makes d the multiplicative inverse of 5 modulo 924. Given two integers, a and b, the extended Euclidean algorithm can be used to find the greatest common divisor of these two integers. It will also give us two other numbers, x and y, that satisfy the equation ax plus by is equal to the greatest common divisor of a and b. So how does this help us? Well, plugging in e equals 5 for a and m equals 924 for b, we already know that these numbers are coprime. So their greatest common divisor is 1. So this gives us 5x plus 924y is equal to 1. Or 5x is equal to 1 minus 924y. But if we only care about everything modulo 924, then we can drop the minus 924y. Think back to the clock. If the minute hand is on 1, and then exactly 10 hours pass, we know the minute hand will still be on the 1. Here, we start at 1 and then wrap around exactly y times. So we'll still be at 1. So we have 5x is equal to 1 mod 924. And here, this x is the same as the d we were looking for before. So if we use the extended Euclidean algorithm to get this number x, that's the number we should use as our d. So now let's run the extended Euclidean algorithm for a equals 5 and b equals 924. We'll use a method called the table method. Our table will have 4 columns: x, y, d, and k. Our table starts off with 2 rows. In the first row, we have 1, 0, then our value of a, which is 5. And our second row is 0, 1, and our value for b, which is 924. The value of the fourth column, k, will be the result of dividing the value of d in the row above it with the value of d on the same row. So we have 5 divided by 924 is 0 with some remainder. So that means we have k equals 0. Now, the value of every other cell will be the value of the cell 2 rows above it minus the value of the row above it times k. So let's start with d in the third row. We have 5 minus 924 times 0 is equal to 5. Next, we have 0 minus 1 times 0, which is 0, and 1 minus 0 times 0, which is 1. Not too bad, so let's move on to the next row. First, we need our value of k. 924 divided by 5 is equal to 184 with some remainder, so our value for k is 184. Now, 924 minus 5 times 184 is equal to 4. 1 minus 0 times 184 is 1, and 0 minus 1 times 184 is negative 184. All right, so let's do the next row. Our value of k will be 1, because 5 divided by 4 is equal to 1 with some remainder. So let's fill in the other columns. 5 minus 4 times 1 is equal to 1. 0 minus 1 times 1 is equal to negative 1. And 1 minus negative 184 times 1 is positive 185. So let's see what our next value of k would be. Well, it looks like we have 4 divided by 1, which is 4. In this case, where we're dividing by 1, such that k is equal to the value of d in the above row, means that we're done with our algorithm. We can see here that we have x equals 185 and y is equal to negative 1 in the last row. So let's now come back to our original goal. We said that the value of x as a result of running this algorithm would be the multiplicative inverse of a mod b. So that means that 185 is the multiplicative inverse of 5 mod 924, which means that we have a value of 185 for d. The fact that d equals 1 in the last row verifies that e was coprimed to m. If it weren't 1, then we would have to pick a new e. So now let's see if Rob has received my message.
When someone sends me an encrypted message, as long as I've kept my private key a secret, I'm the only one who can decrypt the message. To decrypt a chunk C, I can calculate the original message is equal to the chunk to the dth power mod n. Remember that d and n are for my private key. So, to get a full message from its chunks, we decrypt each chunk and concatenate the results. So, exactly how secure is RSA? Truth is, we don't know. Security is based on how long it would take an attacker to crack a message encrypted with RSA. Remember that an attacker has access to your public key, which contains both E and N. If the attacker manages to factor N into its two primes, P and Q, then she could calculate D using the extended Euclidean algorithm. This gives her the private key, which can be used to decrypt any message. But how quickly can we factor integers? Again, we don't know. Nobody has found a fast way of doing it, which means that, given large enough n, it would take an attacker unrealistically long to factor the number. If someone revealed a fast way of factoring integers, RSA would be broken. But even if integer factorization is inherently slow, the RSA algorithm could still have some flaw in it that allows for easy decryption of messages. Nobody has found and revealed such a flaw yet, but that doesn't mean one doesn't exist. In theory, someone could be out there reading all data encrypted with RSA. There's another bit of a privacy issue. If Tommy encrypts some message using my public key, and an attacker encrypts the same message using my public key, the attacker will see that the two messages are identical, and thus know what Tommy encrypted. In order to prevent this, messages are typically padded with random bits before being encrypted, so that the same message encrypted multiple times will look different as long as the padding on the message is different. But remember how we have to split messages into chunks so that each chunk is smaller than n? Padding the chunks means that we might have to split things up into even more chunks, since the padded chunk must be smaller than n. Encryption and decryption are relatively expensive with RSA, and so needing to break up a message into many chunks can be very costly. If a large volume of data needs to be encrypted and decrypted, we can combine the benefits of symmetric key algorithms with those of RSA to get both security and efficiency. Although we won't go into it here, AES is a symmetric key algorithm, like the Vigenère and Caesar ciphers, but much harder to crack. Of course, we can't use AES without establishing a shared secret key between the two systems, and we saw the problem with that before. But now, we can use RSA to establish the shared secret key between the two systems. So, we'll call the computer sending the data the sender, and the computer receiving the data the receiver. The receiver has an RSA key pair and sends the public key to the sender. The sender generates an AES key, encrypts it with the receiver's RSA public key, and sends the AES key to the receiver. The receiver decrypts the message with its RSA private key. Both the sender and the receiver now have a shared AES key between them. AES, which is much faster at encryption and decryption than RSA, can now be used to encrypt the large volumes of data and send them to the receiver, who can decrypt using the same key. AES, which is much faster at encryption and decryption than RSA, can now be used to encrypt the large volumes of data and send them to the receiver, who can decrypt using the same key. We just needed RSA to transfer the shared key. We no longer need to use RSA at all. Looks like I've got a message. It doesn't matter if anyone read what's on the paper airplane before I caught it, since I'm the only one with the private key. Let's decrypt each of the chunks in the message. The first chunk, 658, we raise to the dth power, which is 185. Mod n, which is 989. Is equal to 67, which is the letter C in ASCII. Now on to the second chunk. The second chunk has value 15, which we raise to the 185th power. Mod 989 and this is equal to 83, which is the letter S in ASCII. Now for the third chunk, which has value 799, we raise to 185, mod 989, and this is equal to 53, which is the value of the character 5 in ASCII. And now for the last chunk, which has value 975, we raise to 185, mod 989, and this is equal to 48, which is the value of the character 0 in ASCII. My name is Rob Bowden, and this is CS50. Use RSA at all. RSA at all. At all.
Wait!